Okay, and welcome back. So, we are going to be moving today into chapter 4, which is going to start with some pretty heavy theory, as you can kind of see up here, theory about linear equations. So, um, we have some rather interesting material ahead. Buckle up, it's going to be a little bit complicated, but it won't be too bad. But before we get to that, we're going to knock out the homework that we have from 3.3. So let's go ahead and tackle that first. And to start with, we had for problem 1, let's see, we had a decay chain taking place where x decayed into y, decayed into z, and we were given some initial conditions. We were said that the amount of the x element at t equals 0 was x naught, and that the amount of the y element at t equals 0 was 0, and the amount of the z element at t equals 0 was also 0. So we didn't have any of y or z when we started. We just had the x, but the x is going to decay into y, which is then going to decay into the z element. So last thing we need, though, before we tackle this is kind of something we developed earlier when we were first using the systems of equations to describe the decay chains. We need the differential equations that we came up with. So we had dx dt is equal to negative lambda 1 x. So lambda 1 is going to be the rate at which the element x decays. And then we're going to have dy dt. Well, that's going to equal positive lambda 1 x, because it's going to be receiving the material from x, and then it's going to be giving material to z at a rate of lambda 2 times y. Okay? And so finally we have dz dt. Well, that's just the opposite of the rate that the amount of stuff that's coming from y. So everything that leaves y comes into x, so it's going to be a positive lambda 2 y. Okay? So now that we have that, we have all of our initial conditions, we have the system. It wants some generalized solutions to x of t equals, y of t equals, etc. So let's see if we can figure those out. We're going to start off, we're going to figure out what x of t is equal to. So we have this dx dt is equal to negative lambda 1x, lambda 1x. Alrighty, so I'm going to use separation of variables on this. I'm going to move all the x stuff over to the left side, all the t stuff to the right. So I move x over, I get 1 over x dx is equal to negative lambda 1 dt. Okay, now that I have everything moved on to the appropriate side, I can take the integral of both sides. And when I do that, I'm going to wind up with the natural log of x is equal to, I'm going to have negative lambda 1 t plus c on this side. Okay? Now that I've got that separated off and I've taken the integrals, I can now work on simplifying this. So I'm going to swing up to here. And so now I can apply the exponential to this, and I'm going to wind up with e to the natural log of x is equal to e to the negative lambda 1 t plus c. Okay? And we've talked about before, the way that we handle over here is this is e to the negative lambda 1 t times e to the c. That's how I get this expression up here. I can break this summation into two exponentials multiplied by each other. And so I'm going to call e to the c just c. I'm going to make it a different constant. So this is going to wind up being x is equal to c times e to the negative lambda 1 t. Okay? Now, I need to figure out what this c is. I have a pretty good idea. I can figure out what C is based on running a lot of these. But let's just run through the process. So x at t equals 0, x of 0 is equal to C times e to the negative lambda 1 times 0. Okay? Alrighty. Now, x at t equals 0 is equal to something. That's equal to x naught. So, here we go. I think I can squeeze all this in. I'm going to have x naught equal to, well, e to the 0, which is what this becomes, is just a 1. So that equals my c. So I now know what the constant had to be. I knew that from just working a bunch of these, that this is always your initial amount, but it's good to get verification. So I get my final expression. I'm going to have x is equal to x naught times e to the negative lambda 1 t. And I am going to box this off. Okay? So, and I could also mention, I don't know if I can write it in super tiny in here, but we'll see. This is x at time t, right? This is the amount of stuff at time t. Okay, so far so good. We have now an expression for x of t. Now we need to figure out what y of t is going to look like. So we're going to shift over to the to a new board and see what we get. So here we go. So we're going to start off with some, in the original form I had dy dt is equal to lambda 1 x minus lambda 2 y. Alrighty, I'm going to rewrite this into a prime notation. Okay, so I'm going to change this into y prime is equal to lambda 1x minus lambda 2y. Okay, I'm now going to move this y over to the left side. So I'm going to get y prime plus lambda 2y equals lambda 1x. Okay? Now, I can substitute in my x expression that I just solved for right here. So I'm going to wind up with y prime plus lambda 2y equals lambda 1 times x naught times e to the negative lambda 1 t. Okay? Now, seems like we've done an awful lot over here, but it's not too bad. Does this look like it's in a form? Does anybody recognize this form? I hope so, because I gave a hint in the previous lecture. So this right here is a first order linear equation, and one of our favorite methods of solving those is integrating factor. Absolutely, 100% right. So if I think about the integrating factor, that means that this piece that's in front of my y, I can call that p of t, and then everything that's over here, I'm going to call f of t. Okay? Now, my solution relies on finding mu, and mu is equal to, I've got e to the integral of p of t dt, right? Well, this one's a really easy one to do because p of t is just lambda 2, and the integral of lambda 2 with respect to t is just going to be lambda 2t. So this is just going to wind up being e to the lambda 2t. Okay? That's what my mu winds up being. Alrighty, so now that I have that, I can actually solve for it. So to solve for it, I'm going to put it into the form y equals, we're going to have 1 over lambda, so it's going to be 1 over lambda, 1 over mu, which is 1 over e to the lambda 2t, okay? times the integral of mu e to the lambda 2t bracket times my f of t, which is all this stuff over here. So it's a lambda 1 x naught e to the negative lambda 1 t, and all of that dt. Okay? So if I do that, I wind up with, first thing I want to do is take everything out of the integral that I can. So anything that doesn't depend on t is fair game. So let's see, what can I take out? I can take out this lambda 1 and this x naught. Everything else is bound up with t, so I can't do much with it. So I'm going to move those over. I'm going to wind up with y is equal to, I'm going to swap the order and put it as x naught lambda over e to the lambda 2t on the integral of, this is going to be, only thing that's left is this piece times this piece, right? So I'm going to actually rewrite this as the integral of what that thing is called. So the integral of e to the lambda 2t times e to the negative lambda 1t dt. Okay? Now, you can already see what's going to happen. I'm going to combine these and get y equals x naught lambda e to the lambda 2t times the integral of e to the, here we go, parentheses, lambda 2 minus lambda 1 t dt. Now I can do this one. This one's not too bad. When I integrate e to the something t, since I'm integrating, I'm going to wind up with 1 over that something, right? So let me take the integral now. I'm going to wind up with y is equal to x naught lambda 1. I can't forget my lambda 1. That was lambda 1, right? 1, 1. Don't let me drop my subscripts. Yell at me through the screen off. I promise I'll hear it. So over e to the lambda 2t. Alrighty, so this integral becomes bracket 1 over lambda 2 minus lambda 1 e to the lambda 2 minus lambda 1 t plus c. Alrighty? So that's where we are, and that's where we're going to start on the next page. So, I mean, I could put a line right here, but it'd be squished, and I'd rather go ahead and switch to the next page. So here we go. Clear the screen, and we're going to start with that. I'm not going to do anything before we have that rewritten. So y is equal to x naught lambda 1 over e to the lambda 2t times bracket 1 over lambda 2 minus lambda 1 times e to the lambda 2 minus lambda 1 t plus c. Alrighty? So I've got this expression here. Now, it seems like a good idea if I would multiply through by what's here, but before I do that, I'm going to break this back into its exponentials and take this term and move it over. All right, so I'm going to move a few things around. So here we go. Y is equal to, I'm going to have x naught lambda 1 over lambda 2 lambda minus lambda 1. And then I'm going to have that multiplied by this thing, 1 over e to the lambda 2t times, I'm going to have e to the lambda 2t times e to the negative lambda 1t. And then all of that, I'm going to have plus c times 1 over e to the lambda 2t. Lambda 2t. Because I'm distributed, right? I took this e to the lambda 2t and multiplied it by the c. So I can't forget that I have that. Alrighty? So you can already see what's going to happen. I've got 1 over e to lambda 2t times e to lambda 2t, and so these two are going to become a 1. So I'm going to have y is equal to, I'm going to have x naught lambda 1 over lambda 2 minus lambda 1. And then what's going to be left over here? Well, not much. It's just going to be bracket e to the negative lambda 1t plus, I'm going to have c times e to the negative lambda 2t. And that's actually kind of nice. Okay? So, now that I've got this expression into this form, what I need is my c right here. Okay? So c can be found using my initial condition. I know that at t equals 0, the amount of y that I have was 0. So 0 is equal to x naught lambda 1 over lambda 2 minus lambda 1 times, well, this is going to simplify, e to the 0, it's just going to be 1. E to the 0 is going to be 1, so 1 plus c, like that. Okay? Now, this is the fun part. This whole thing has to be equal to 0. But the only way that this whole thing is equal to 0, no matter what I start with for my initial amount, is going to be if c equals negative 1. So c equals negative 1. Has to be, in order to make this whole thing equal to 0. So now I have my expression for y, and I'm going to write that. I guess I can get away with it right here, maybe. No, I'm going to go to the next page and do that. So here we go. So y is going to equal, here we go, x naught lambda 1 over lambda 2 minus lambda 1, okay, times bracket e to the negative lambda 1t minus, because the c is a negative 1, e to the negative lambda 2t. And that is our expression for y of t. Whew. Like I said, it's a lot of work to get there, but we can get there. Just a little bit of math. Oh, the fun we're about to have. So much fun. So that was, I don't know why I did that string mark, but ignore that. This is our expression for y of t right here. All right. Now, I think I went off the board. Now we have to find z. And z is going to be a little bit odd because I'm going to do separation of variables with this. So I've got dz dt is equal to positive lambda 2y. Okay? Y is equal to all this. So dz, and I need to put my little marks in to make sure you can know that's a z. dt is equal to, here we go, lambda 2 times all the stuff that's up here. X naught lambda 1 over lambda 2 minus lambda 1. And then that's multiplied by e to the negative lambda 1t minus e to the negative lambda 2t, like that. Okay? So I'm going to separate variables. I'm going to move all of the stuff that is z over on the left and everything that's t over on the right. And what do you know? dz equals lambda 2 bracket x naught lambda 1 over lambda 2 minus lambda 1 times e to the negative lambda 1 t minus e to the negative lambda 2t dt. That's what it becomes. There's nothing else we can move over. There are no z's here. And see, this is why I put that little crossbar, because my 2's look like z's an awful lot. But if it has the crossbar, it's a z. Otherwise, it's a 2. So now that we have it separated, we can take the integral of this. Okay, integral of dz is just z. So z equals, and this looks just terrible, but it's not horrible because all of this stuff right here does not depend on t. None of it does, right? So this can be taken out of the integral, and I can do these integrals because these are just simple exponentials. So it's going to equal, I'm going to go ahead and distribute this lambda 2 in for this term. So this is going to be x naught lambda 1 lambda 2 over lambda 2 minus lambda 1. And I can see I'm getting very near the bottom of the page. So let me actually go to a different one. Let me start back over with that z. So z equals, we're going to have x naught lambda 1 lambda 2 over lambda 2 minus lambda 1, okay, times, well, the integral of e to the negative lambda 1t is just negative 1 over lambda 1 e to the negative lambda 1 t, and the integral of e to the negative lambda 2t is just negative 1 over lambda 2, but it was a minus sign in between, so the minus minus are going to cancel, so it's going to become plus 1 over lambda 2 e to the negative lambda 2t plus c. Okay? So that is what we get after we take the integral. And so now everything else is going to be a whole bunch of algebra and plugging initial conditions in. So here we go. We wind up with, I'm going to factor out my x naught completely out of here. So I'm going to get z is equal to x naught times lambda 1, lambda 2 over lambda 2 minus lambda 1, like that. And then I'm going to have over here everything that I have. So it's going to be minus 1 over lambda 1 e to the negative lambda 1t plus 1 over lambda 2 e to the negative lambda 2t. Alrighty, now here's a slight leap of faith because c times all this over here, which is also a constant, is just another constant. So I'm going to call that plus c right on the outside like that. Okay? Now that I have all of this, I need to figure out what this c is. So to figure out that c, I need my initial condition. So z at t equals 0 is equal to 0. So 0 is equal to, here we go, I'm going to have x naught times lambda 1, lambda 2 over lambda 2 minus lambda 1, okay? And then times inside of here, t is 0, so this becomes a 1. So this is negative 1 over lambda 1. This becomes a 1 plus 1 over lambda 2 plus c, okay? Now, I'm going to do some rearrangements here in order to get things to all work out. First thing I'm going to do is find a common denominator for this. Common denominator is going to be lambda 1, lambda 2. So let me go ahead and do that. So 0 equals x naught times, we're going to have lambda 1, lambda 2 over lambda 2 minus lambda 1 times. Alrighty, so this is going to be, if my common denominator is lambda 1, lambda 2, that's just going to become negative lambda 2, and then plus lambda 1 over lambda 1, lambda 2 plus c. And so you can already see what's going on. If I take a negative out of this, if I change this into like a negative on the outside, which I'll try to squeeze in right there, now I can change the signs. This will become positive. This will become negative, so I can erase that. And now what do I have? I've got lambda 2 minus lambda 1 over lambda 1, lambda 2. That is exactly what I have here. So cancel, cancel. And what am I left with? Negative 1. So 0 is equal to negative x naught plus c. So what does c have to equal? C has to equal x naught. Okay? Now, I have to write that up here and to get its final form. Alrighty? So let's see. Let me clear this and go to the next page. So here we go. We're going to have z is equal to x naught times, I'm going to have lambda 1, lambda 2 over lambda 2 minus lambda 1 bracket. Inside of here it's going to be negative 1 over lambda 1 times e to the negative lambda 1 t plus 1 over lambda 2 times e to the negative lambda 2 t, and then plus my constant, which is x naught. Alrighty, so I can rearrange this a little bit more and get it into a nice final form where the x naught will be in one location. So if y'all are ready to do that, I can knock that out. So here we go. First things first, I am going to distribute this through this expression, okay? So if I do that, I'm going to get z is equal to x naught times, here we go, bracket. If I send this and multiply this, so my lambda 1s are going to cancel, I'm going to be left with negative lambda 2 over lambda 2 minus lambda 1 e to the negative lambda 1 t plus, when I multiply this factor by this coefficient here, I'm now going to cancel lambda 2. So this is going to be lambda 1 over lambda 2 minus lambda 1 e to the negative lambda 2 t bracket plus x naught. Now, I am almost there. If I want to factor an x naught out of everything here, this will become a 1. So z is equal to, here we go, x naught factored out of 1 minus lambda 2 over lambda 2 minus lambda 1 e to the negative lambda 1 t plus lambda 1 over lambda 2 minus lambda 1 e to the negative lambda 2 t. Bam. That right there is your final expression for z of t. Right there. Woo! That was a 30-minute derivation. Like I said when I assigned it, this takes some doing. This is a lot of work to get there. But I hope you're at least somewhat excited that we started off with absolutely nothing other than initial conditions, and we knew that we had a decay chain going on. And by doing a lot of math, we can now figure out what the amount of x at time t is going to be, y at time t, and z at time t. All we need in order to do that are the lambda 1 constants, the lambda 2 constants, and how much of x we start with. And that will give us how much y we have, how much z we have, and how much x is remaining at any time t. So although it was an awful lot of work, I think this is extremely satisfying that we went from such sparse information to expressions that we can actually use, plug in our real transition rates, and get an actual answer out. So kind of cool. Alrighty. So, but wait, there's more. That was just the first one. So let's knock out the next homework. I'm going to clear this and we can get started. So here we go, clearing away. Okay, so for number 5, we have, um, let's see, it is potassium 40 that is decaying. And so potassium 40 decays into 2 elements. Most of it is going to decay into calcium 40, and that's through, what is it, beta decay maybe? Yeah, beta particle emission, yeah. And then some of it also decays into argon 40, and it does that through electron capture. And electron capture is above my pay grade. I didn't do any of the neutrino work back when I was doing some of the radioactive stuff for my PhD. So, anywho, kind of cool stuff. If you want to read up on it, I highly recommend it. Although, be prepared, it gets pretty deep pretty fast. But anywho, so all we know is that we have um, the potassium. So K is potassium, right? So we're going to have K for potassium. And then let's see, I think we're going to say calcium is going to be represented by C. And then A is going to be argon. Just so we can keep everything straight. And we know that the potassium decays into both calcium and argon. So we're going to have, oops, I want to do that. We're going to have decay dt is equal to, we're going to have, it's going to be a negative because it is losing material. And so it's going, what is it, how fast is it losing the material? Well, we're going to call the transition from potassium to calcium lambda 1. So this one is going to be lambda 1. And this one to argon is going to be lambda 2. That's going to represent the rates. Okay? So dk dt is going to be negative lambda 1 plus lambda 2 times k. Right? And then dc dt is going to be, we said that it had lambda 1, so it's going to receive positive lambda 1k, and dA dt is going to be positive lambda 2k. All right, so we have 3 differential equations, and we're now going to try to solve everything. Only thing that we're going to have, let me see, make sure that's correct. Alrighty, so we're going to say, kind of like we did on the last problem, that the amount of potassium at time equals 0 is K naught, and we're going to start with 0 for the amount of calcium and argon. So the initial conditions are going to be K at T equals 0 is K naught, and C at T equals 0 is equal to A at t equals 0. Both of them are equal to 0. Alrighty? So here we go. We're going to do the exact same process that we did for the last one. We're going to find expressions for K of t and then D of C and A of t. Let me say that again. Or K of t, C of t, and A of t. Okay, I think I said it right that time. So we're going to start off. We're going to solve this expression right here. This is going to be the very first one. So I've got dk dt is equal to negative lambda 1 plus lambda 2 k. Okay? And so I'm going to do separation of variables. I'm going to wind up with 1 over k dk is equal to negative lambda 1 plus lambda 2 t dt. Hold on, that is not supposed to write that. dt over here. Okay, so now that I have them separated, I can take the integral, and it's not going to be too bad, right? This is very familiar territory. So when I take the integral, I'm going to wind up with the natural log of k is going to equal, well, I'm going to have negative lambda 1 plus lambda 2 t plus c. Okay, when I apply the exponential, I'm going to wind up with k is equal to c times e to the negative lambda 1 plus lambda 2 t, right? And so when I do t equals 0, and then the amount of k at t equals 0 is k naught, I'm going to wind up with k naught is equal to c. So my expression is going to be k equals k naught times e to the negative lambda 1 plus lambda 2 t. And this makes an awful lot of sense when you stop and think about it. I've got the rate of 1, the pathway that it transitions from potassium to calcium, and then the rate of the other, potassium to argon. If I add those two rates together, that is the exponential rate at which the potassium is decaying, and I start with some k naught. So this expression right here makes an awful lot of sense. So I'm happy with that. Alrighty. So now let's work on dc dt on the next page. So dc dt coming up. Here we go. So I've got dc dt is equal to, I've got lambda 1k, right? So lambda 1, but what was k? K was k naught e to the negative lambda 1 plus lambda 2 t, right? Okay, so I can now separate that. When I do that, I'm going to wind up with dc is equal to lambda 1 times k naught e to the negative lambda 1 plus lambda 2 t dt, right? Okay, well I can actually solve that. I can take the integral of both sides. That's not too bad. So k naught and lambda 1 are both constants, so they can kind of come out. This is going to wind up with c is equal to k naught times lambda 1 times, here we go. Well, what is the integral of e to that? Well, it's 1 over that factor right there, right? So negative lambda, well, I'm sorry, 1 over lambda 1 plus lambda 2, like that. And then that's times e to the negative lambda 1 plus lambda 2 t. And then I don't want to forget plus c. Little c, not big C. Big C is calcium, little c is the constant, okay? So now if I take this lambda 1 and kind of roll it into all this stuff, I'm going to wind up with c is equal to let's see, k naught times, here we go, negative lambda 1 over lambda 1 plus lambda 2 times e to the negative lambda 1 plus lambda 2 t plus c. Okay? Now that I've got it into this form right here, I'm going to do that same kind of trick that I did before. And I need to do one thing that I haven't done, which I need to be very careful with. When I sent this lambda 1 through, that lambda 1 got multiplied by this constant. Well, I'm going to call that another constant. And now in the next stage, I'm going to call this k naught, which is a constant, times c, also a constant. So I really wind up having, if you will allow me to kind of erase this just a little bit to put into a form that I like a little bit better, something that looks like this, right? So this is what I need to figure out what it is using my initial condition. So I know that at t equals 0, the amount of calcium was 0. So 0 is equal to, I've got k naught times all of this stuff. Well, if I put a t in here, this is a 1. So this just becomes negative lambda 1 over lambda 1 plus lambda 2, and then plus c, like that. Okay? So what does c equal? Well, the constant is going to equal this thing right here because it has, well, it's going to be opposite in sign, but it's going to be positive k naught times lambda 1 over lambda 1 plus lambda 2. That's what it has to be, right? So now I can rewrite this and say that, here we go, final solution coming up. Dun, 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 dun. C equal, big C. I now have my constant, my C, that was at the very, let's see, where did I put my C? I'm looking at my paper now. Da, 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 da. Da, 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 da. Okay. Oh boy, I did a lot of work. Through the magic of algebra, I skipped like 5 steps on my paper and I don't want to figure out what I did. If you will allow it, I promise it follows the same pattern as the last one. Um, I guess I can do it it's not that much. So C is equal to, I've got K naught times, I've got negative lambda 1 over lambda 1 plus lambda 2 times e to the negative lambda 1 plus lambda 2 t, right, plus my c, which is k naught times lambda 1 over lambda 1 plus lambda 2. So it's not too bad, because now I can factor out k naught times this stuff, because they have, both of those have that in common. So if I factor out this, I wind up with C equals, let's see, K naught times lambda 1 over lambda 1 plus lambda 2 times 1 minus e to the negative lambda 1 plus lambda 2 t. Okay, 2 steps of algebra. That's not too bad. Alrighty, now, if you flip back or look, think back to what we did before this, we had that C was equal to, dC dt was equal to lambda 1, okay, and that dA dt was equal to lambda 2, okay, right? So if I do the whole process over again, it is going to look identical to this one, except for a single change. This lambda 1 will become a lambda 2 for A. So A is going to equal K naught lambda 2 over lambda 1 plus lambda 2 times 1 minus e to the negative lambda 1 plus lambda 2 t. Alrighty? So I have my three things that I can work with. I've got my k of t, my c of t, and my a of t. Because all of these have the little sub t, right? That's really what it is. It's the amount at time t. Okay, so now that we have all those expressions, we can work and solve some problems. So first thing I'm going to do is clear this and rewrite my K naught and all of that stuff. Okay, so let's see what we have. Let's see, clear this. My K of t was equal to, let's see, K of t was equal to K naught times e to the negative lambda 1 plus lambda 2 t. Okay, now for the problem, let's see what it wants. It is known that lambda 1, it's going to give us, this is for part A, it's going to say that lambda 1 is equal to, let's see, 4.7526, 4.7526, that's a 2, and times 10 to the negative 10. Okay, and lambda 2 is equal to 0.5874 times 10 to the negative 10. Okay, now let's see. It wants us to find the half-life of K40. So we want to find the half-life of the potassium. So the half-life occurs when this amount over here is 1/2 of what we started with. So all I have to do to solve this is going to be 1/2 K naught is equal to K naught times e to the negative. And now I've got these constants, right? So 4.7526 times 10 to the negative 10 plus 0.5874 times 10 to the negative 10 t. Okay? K naughts are going to cancel. I'm going to be left with 1/2 is equal to this. I'll wind up doing the natural log. And when the dust finally settles, let's see what I get. Let me turn this page. I'm going to wind up with, gosh, t, is it, y'all are okay with solving that. I'm guessing that's not a rough one to solve. I'm going to wind up with t is equal to the natural log of 1/2 divided by this stuff that was added together, which wound up being negative 5.34 times 10 to the negative 10, something like that. I want to solve out, that is approximately, ooh, nice, 1.298 times 10 to the 9th years. Wow, that is a long half-life, which is not surprising since the rates are so small. It's sort of, that makes sense. But what is that, 1.3 billion years, something like that? Considering the whole universe didn't say nearly 14 billion years. So I have to do the Big Bang Theory song to remember how old the universe is supposed to be, something like that. So it's a substantial fraction of the entire lifetime of the universe before we hit the half-life. So that's kind of cool. Now, the second part, it wants to determine the percentages of the amount of K that decays into Ca and the percentage of K of potassium that decays into argon, just say the words, over a long period of time, basically as T goes to infinity. So what we're going to do is we're going to use our equation that we set up for C and for A and solve each of them and hopefully get something that agrees. So here we go. I'm going to clear this, and we had C of T was equal to lambda 1 over lambda 1 plus lambda 2 times K naught 1 minus e to the negative lambda 1 plus lambda 2 t. Whew. Okay. Now, that's if I do all this out, I'm going to wind up with something that looks like at t goes to infinity. Well, when t hits infinity, this is e to the negative infinity. So anything e to the negative infinity, that's basically 1 over e to the positive infinity. 1 divided by an infinity is 0. So this whole expression here goes to 0. Okay? So I'm left with just this expression right here because the only thing that's left is 1. So I get this ratio as t goes to infinity. So C is equal to lambda 1, which was that 4.7526. Well, that was really nicely written. I was looking away, so let me make that look a little bit better. 4.7526 times 10 to the negative 10 over 4.7526 times 10 to the negative 10 plus, what was it, 0.58, 0.5874 times 10 to the negative 10. Alrighty, when I do that ratio, I'll wind up with 0.89 K naught. So 89% of K naught becomes calcium. And then if I do the same with A, I'd better wind up with something complementary because all that changes with A is now I'm going to have 0.5874 times 10 to the negative 10 on top of all of this stuff. And when I do that one, I wind up with what I should, which is 0.11 K naught, which is around 11%. If I had reached any other value, I would have been pretty shocked. So this is not surprising whatsoever. I mean, when you think about it, if I multiply this rate by 9, I get this rate. By 9, by 8, I get this rate, which 89, 11%. That means it was a roughly that kind of ratio. What does that be? 8 to 1, 9 to 1, whatever it is. I'm trying to do the ratio of 89 over 11. That's about a 9 to 1 ratio, which is about what it looks like if you just kind of glance at these two values. So it's no shock there, but it's nice to know that as an infinite amount of time passes, we are going to have 89% of all potassium, 40 becoming calcium, and 11% becoming argon. So there you go, in case you wanted to know. Alrighty, so that was homework number 2. That's much better. That was only 23 minutes, so not too bad. All right, so let's clear this and start tackling some of the theory from chapter 4. So here we go. Magic of clearing and starting. I would take a break if I were y'all. So here we go. Okay, so here we are back again. I changed my mind. I'm gonna let y'all go after this. So we'll start in on chapter 4 in the next video because I'll only be able to get half a page down before we hit the hour 25 limit. So anywho, hope you enjoyed the problems. This is just a little bit of tail end on that. We'll start I should have the 4-1 up pretty quickly because I've already prepped for it. So it won't be too bad. But right now my brain is mush. I'm sure your brain is mush. I will see y'all later. That's the worst exclamation point anyone's ever done. So y'all have a good one, and I will see you in a little bit. Bye-bye.